Well, I haven't made a video in quite a while, but recently I read a paper that made a claim that I think I would like to highlight, because I think it provides an argument for my case of not crossing the event horizon. Now, I've always said, oh, you don't cross the event horizon, don't cross the event horizon. I've just basically attributed that with using special relativity equivalence to general relativity to say that light cones close at the event horizon. But there's more to it than that, because just going below the event horizon is one question. What lies below the event horizon itself is another. And the argument will break down if the space below the event horizon can actually allow for further falling into the singularity. So I wanted to say something about this paper, which I read, and the one claim in it that I'm really trying to debate is the claim that more space exists within a black hole than the volume of a standard two-sphere of equivalent size. What I'm basically saying is that there's more space than should be inside a black hole. That's the claim the paper is making that I want to demonstrate, I think, supports my hypothesis, and even though some other claims in the paper obviously refute them. I'll put a link to the paper, and you can make up your own minds. I want to lay out, okay, what does it mean by there's more space under an event horizon and inside a black hole than should be in that standard volume? Well, I got some paper craft here that I've made to illustrate the idea of space and curvature and having more or less space. So we'll start with the simplest one. This is just a flat piece of paper. It's a flat disk. Each of these were based on the same type of paper, the same size, circle. And this is just what all the paper craft you see before you was made out of. It starts with this flat piece of paper. And this is flat space, you could think of it. And we won't be talking about volume, obviously, but I want you to imagine area on these paper surfaces as equivalent to volume, so having more or less area or volume represented in 2-dimension rather than 3. If I'm a light beam and I'm traveling across this piece of paper, I go straight across because the paper is flat. There's no curvature at all to the paper. So light travels across it flat. This is a cone. This is a paper cone. This was made by giving the cone less space than its counterpart, or less area, basically. What you do is you cut a pie section out of the paper disc like this, and you can connect it, and I've taped it up. So this has less surface, less area than this. This has more area. And what happens to a light beam as it's crossing this in this representative space? It's bent. And it's bent in such a way that it moves towards the curvature at the center. And because that bending towards it, we can say, okay, there's positive curvature on this surface. And we see gravity as positive curvature as well. We know this because we see light beams bent towards gravitational sources. And it's important to remember that this cone has less surface area, or if we were to move it up to 3D space, less volume than flat space. But what happens when we get more space than would be allowed in the flat space model? We get something like this. This, I've taken a pie-shaped piece of paper, and while we took one out of this piece of paper, we put it into this. So this has more space than should be allowed for its particular arrangement. And what that does is it curves the space in such a way that it has a negative curvature. You can see the negative curvature like this. The arcs of these two curves go up, and the arcs of these two curves go down. And my hypothesis is that below event horizons, the space becomes pseudospherical, and pseudospheres are negatively curved, so they look like this. What happens when light beams travel across the negatively curved surface? They curve away from the curved source. So while we have attractive space curvature here, we have repulsive space curvature here. So what I'm putting forward is, if the claim is to be made that there is more space beneath the event horizon than flat space, thus producing a greater volume inside the black hole than should be allowed for a sphere of the black hole size, that would negatively curve the space. So even if you could get under the event horizon, you'd find negative space-time like this, in which light beams are pushed away from the curvature. Thus meaning you don't fall anywhere below the event horizon because the curvature doesn't allow for it. Recently I saw a discussion, it's actually a lecture by several physicists, and one of them, Dr. Mather, put forward, if you don't fall through the event horizon, there's really no information paradox. A lot of problems get solved if the case is that you don't cross the event horizon. Of course, this professor, he doesn't recognize that you don't fall below the event horizon because we've been using Eddington-Finkelstein coordinates to basically say, well, light cones close in a way that allow us to go below the event horizon, even though they don't have an equivalent in the principle of equivalence. There's no Eddington-Finkelstein light cones in special relativity is what I basically mean. So you can't have equivalence between the two, so the principle of equivalence is being violated. But setting that aside, if you use this simple geometric idea and the claim is made that below the event horizon there's more space than should be allowed, then I think it's not even remotely impossible to make the argument that that means the space below it must be repulsive to light. Gravity must be a repulsive force, not an attractive force. And if you do that, suddenly you're at the gate of ending the information paradox, because nothing can cross the event horizon because there's nowhere to go, because the space is pushing you out of it. Now there's a lot of other ideas in my hypothesis, but I think if you just conceive that, all right, I'm saying that you don't cross the event horizon, and I'm saying that space-time is negatively curved, and knowing that there's a paper that says, you know what, there's more space than should be inside this sphere, this spherical black hole, that gives credence to the idea, all right, well that means that space probably looks negatively curved if it's functioning in this simple geometric way. May not be, but I still want to put this forward. And there'd have to be a pretty big, there'd have to be some other drastic explanation, I believe, to explain away the idea of falling inside the black hole when I think clearly everything just points to, no, it doesn't. There's no way below the event horizon. You know, your proper time is 0 at the event horizon. The space-time below it should be negatively curved and repulsive. And if you look at a black hole, it has the layout of a hyperdimensional pseudosphere, that being a manifold surface with a singularity in the center of it. It's just like looking at a pseudosphere from the mouth end at all times. Now, there is another way of looking at it. If I looked at this from the top, this is a cone. If I look at just a cone from the top down, I would just see a circle and a singularity as well, because the singularity is at the peak of a cone, just as it exists in the center of a pseudosphere. However, it would really come down to what is the manifold surface below the event horizon. And if it's negatively curved, then I have no problem with saying that below the event horizon, space is negatively curved, hyperpseudospherical, and there's no way to fall down into the singularity because the space-time pushes you out.